All right, welcome to the Explainer. If you're trying to wrap your head around the mathematics and the architecture behind generative AI, you are absolutely in the right place. Consider this your high-yield ultimate study guide for mastering generative loss functions. We're skipping the beginner fluff today and diving straight into the optimization dynamics that actually make these models tick.
Here's the syllabus for our cram session today. First, the vanilla baseline. Second, fixing adversarial loss. Third, perceptual and feature losses. Fourth, frequency and contrastive advanced. And finally, number 5, the ultimate exam cheat sheet. Let's get to it.
Section 1. The vanilla baseline.
So at its core, the vanilla minimax GAN is basically a high-stakes, game-theoretic optimization. The entire goal here is to minimize the Jensen-Shannon divergence between the real data distribution and the fake data distribution that the model generates. It is a literal game of cat and mouse between a generator trying to create hyper-realistic data and a discriminator whose only job is to catch the fakes.
Now look at this architecture here. The discriminator processes the input through convolutional layers, down to a dense layer, and finally hits a sigmoid activation. Traditionally, this just outputs a simple single probability, right? Just a number between 0 and 1 declaring, hey, is this image real or is it fake? It's a super elegant setup, but as we know, it comes with some serious mathematical baggage.
Okay, time for our first flashcard. Think about this. It's a classic exam or interview question. What happens when the discriminator gets too good, too quickly, during that early training phase?
The short answer? Total optimization failure. See, if the discriminator easily spots the fakes, its sigmoid output completely saturates. And when that happens, your gradients vanish. That means the generator gets absolutely zero useful feedback to improve itself. This leads directly into severe mode collapse. The generator essentially gives up and just produces the exact same limited set of images over and over again, mostly because that Jensen-Shannon divergence is fundamentally discontinuous.
Section 2. Fixing adversarial loss variance.
First up, we have a brilliantly simple fix. The original minimax loss relies on cross-entropy, which is sharp and, like we just talked about, saturates way too quickly. Enter the least squares GAN, or LSGAN. It replaces that cross-entropy with a mean squared error, or L2 loss. By penalizing the square distance from the target labels, it suddenly provides smooth gradients. It literally drags those outlier samples smoothly toward the real data manifold. Boom, vanishing gradients fixed, and you didn't even need complex architectural changes.
But if you really want the ultimate architectural fix for mode collapse, you need the Waterstein-Ghon, or WGN. Instead of Jensen-Shannon, WGN minimizes the Earth mover's distance. Think of it like calculating the exact minimum cost to literally shovel and transport mass from the fake distribution to perfectly match the real one. Because of this, it replaces the binary discriminator with a critic that outputs a raw, unconstrained score. The absolute beauty of this math is that it's continuous and differentiable everywhere.
Now here's a crucial pro tip for your exam regarding WGAN implementations. The theoretical math requires the critic to be a one-Lipschitz function. The original WGAN forced this using weight clipping, just brutally clamping weights to a tiny box. But honestly, weight clipping is terrible. It forces the network to learn overly simplistic functions. Luckily, WGAN-GP fixed this elegantly. It introduced a gradient penalty, meaning it penalizes the model anytime its gradient norm deviates from 1. The result? Incredibly robust convergence.
Section 3. Perceptual and feature losses.
Next flashcard. This is a very common troubleshooting scenario, so think about this one. If you're training a super-resolution model using a standard L1 or L2 loss, why does the output almost always look blurry and washed out?
Well, it all comes down to a fundamentally flawed assumption in pixel-wise loss. L1 and L2 losses calculate the difference between raw pixels at the exact same localized coordinates. They falsely assume that every single pixel is spatially independent. So when the network is faced with any uncertainty, it hedges its bets. It just averages out all the plausible pixel values. And the result is a perfectly safe but entirely smoothed out blurry image that completely lacks any crisp high-frequency textures.
So to fix that blurriness, we pivot to perceptual loss. Instead of comparing those raw pixels, perceptual loss takes both the generated image and the target image and passes them through a pre-trained network, usually something like a VGG classification model. Then we measure the distance between the high-level feature maps inside that network. If the internal activations match, it means the structural and semantic details match. It's actually exactly how human perception works.
But highlight this golden rule in your notes.
Deep perceptual losses do not follow standard transfer learning conventions. In normal transfer learning, you always want the deep, final layers, right? But for perceptual loss, you absolutely need the features from the early to mid layers. Why is that? Because the later layers in a VGG network actually throw away localized geometric details so they can focus purely on classification. If you use those late layers, your image synthesis will totally fail to capture the correct spatial geometry.
Section 4. Frequency and Contrastive Advanced. All right, troubleshooting time again. Imagine you're evaluating your model's outputs, and you start seeing these artificial, grid-like checkerboard patterns baked right into the image. Spatial objectives can't fix this because the error exists purely in the frequency domain. So, how do you fix it? The answer is focal frequency loss, or FFL. FFL utilizes a 2D discrete Fourier transform to explicitly map the image directly into the frequency domain. And the really clever part is its dynamic weighting scheme. It automatically downweights the easy low-frequency data, which literally forces the network to focus heavily on the difficult high-frequency details. This directly wipes out those artificial patterns and recovers hyper-realistic textures.
Now look at this classic example right here, translating a horse into a zebra. The massive catch here is that we don't have paired data. We don't have a perfectly matched photo of that exact horse painted with zebra stripes to use as a target. So how on earth do we ensure the background and the posture stay exactly the same?
We pull this off using patch NCE loss. It is a brilliant contrastive learning framework. Instead of requiring this massive memory overhead to enforce full cycle consistency, translating the zebra all the way back to a horse, patch NCE just takes random patches of the input image and maximizes the mutual information with the exact corresponding patch in the output image. It essentially pushes the output to match the structure of the input patch while simultaneously pushing it away from random other patches in the image. It's a highly efficient, one-sided unpaired translation.
Section 5. The Ultimate Exam Cheat Sheet.
Okay, get ready to screenshot this. Let's break it down one last time so it really sticks. Starting with the classic, vanilla Minimax gives you unsupervised mapping via Jensen-Shannon. But remember, you risk that dreaded mode collapse. To fix that, you step up to WGANGP, which brings in incredibly robust smooth gradients by optimizing the Earth mover's distance. Alternatively, LSGAN fixes those vanishing gradients using simple Pearson chi-squared L2 math. Now, when you want outputs that actually align with human vision, perceptual loss steps in, preventing blur by comparing deep activations. And finally, for translating images without paired data, patch NC is your go-to, achieving that by maximizing mutual information. Seriously, master this grid and you master generative loss architectures.
I'm going to leave you with one final provocative thought. Basically, everything we've discussed today was born in the era of convolutional neural networks. But as the entire field rapidly transitions to massive transformer backbones for image generation, we really have to ask, will these specific convolutional loss functions continue to dictate visual realism, or are we standing on the horizon of an entirely new mathematical paradigm for perceptual similarity? It's a pretty exciting frontier to think about as you continue to explore beyond this guide. Thanks for hanging out and learning with me today.